will tell us about efficient quantum thermal simulation, Gibbs sampling. Thank you. Fernando, please.
Thank you. Can you hear me? Yeah. Yep, okay. Thanks the organizers for putting this together, for inviting me. I'm very happy to be here. I think the theme of the workshop is great, right? So it's like, I think, energy, well, okay. You can connect energy to anything, right? So it's a bit easy to say that, but I do think energy is very, very strongly connected, right, to quantum information, quantum computation. It goes to the early days, right, or to the pre-days of quantum information, right, with, as we saw in the first talk, right, with studies of Maxwell Demon, right, and thermodynamics. Once you go to, like, the fundamental limits. Of course, quantum, like energy, will be a crucial point if you actually want to build quantum computers that work, right, with error correction and, the current estimates. If you just scale up hardware, right, with many platforms, they're quite daunting, right, to get the quantum computing to work just because of energy considerations, right? And I think there'll be some talks about this here. So it's kind of a waking up call, right, that we do need more efficient ways to build quantum computers, but also we might need to, maybe the first quantum computers will require like a nuclear plant next to it, right, to make it work. So energy will be a big consideration there. And another, I think, important connection of quantum computing and energy is that we hope, right, that some of the future applications of quantum computers will be relevant to develop better methods, right, to produce energy, to store energy, right, so to create like new technologies around energy. And that's, as everything in quantum applications, right, there's a lot to figure out. We don't really know it, but there's some ideas. And the talk that I want to give is about some of these ideas, right? So how we might use quantum computers to learn more about, developing new ways to store and to produce energy, but more generally about like how we can, use quantum computers to simulate physics, and in particular thermal physics in this talk. So this is joint work with 3 people. So with Anthony Chen, he was my student at Caltech. Now he's a postdoc at Berkeley. With Mike Castoriano, who is faculty in University of Copenhagen, and Andreas Gillian, who works at the Rennes Institute in Hungary. And we all did this work together as part of Amazon Web Services, the quantum computing initiative that we have there. All right. So why we're interested in quantum computation, right? Well, it's because first, there is this old thesis, right, in computing, the strong church-Turing thesis, which says the following. It says that any physically realizable computing model can efficiently simulate one another. What efficiently means? Well, it means that, okay, maybe one model, right, maybe you want to, with your cell phone, you want to do something that a universal Turing machine would do. There might be a slowdown, but this slowdown is not too big, right? Let's say it's a polynomial in the system, is the input size of the system, or of the problem, is low down. So it doesn't matter what you're using, right? The fundamentals of computing is the same, right? It's all like you can model as a Turing machine or some circuit model, whatever you want to do. And this seems to be true for every model of computation that we know, except one, right? Quantum computing, right? So we believe, we cannot prove it, but we strongly believe that quantum computing violates the strong Church-Turing thesis. And what this means, right, concretely, it means that for some, let me try to use this. It was always a bit challenging. Wait, where is the hand? Oops. Maybe because this presentation mode doesn't work? Huh. You can see like this. Yeah, I can use this one. It's fine. So what it means? Well, it means that we believe that for some problems, right, not for every problem, but for some problems, quantum computing gives exponential speed up over classical computing. So that's very exciting, right? So what it means is exponential speed up, where it can be, of course, in time, right? Sometimes it can be in space, like number of, bits versus qubits. It can be, of course, in energy, right? That you need to solve a problem. So this is very relevant, of course, but the question is for which problems, right? So when we have this quantum advantage, right? When quantum computers help, and that's kind of what if you ask this to researchers in quantum algorithms, that's what they do, right? Like these monkeys, because we don't really know, right? Many problems. It's like an open question, really for which problems and if there's relevant problems. We know a little, but not too much, right? So of course we know the early examples. The whole field started, right? Oh, Shor should have been 94 here. It's a typo. So we know from work by Shor in 94 that we can break public crypto, right? We can break RSA, we can break elliptic curves and many other protocols that we use today for encryption. So because there's a huge amount of investment, right, in breaking these protocols, they could not be broken so far. So that's very good evidence that quantum can give exponential speed up for some problems. This might have, of course, a lot of economical value if this can be done. But of course, now there is this transition to post-quantum cryptography to try to protect our secrets. But that's, of course, a great example, very well known. There's a second one, which is Grover, right, from 96, and just search, right? Whenever you can map your problem to some kind of search, quantum can help, but you have just a quadratic speed up, right? And this quadratic speed up might not be good enough. First, maybe just quadratic doesn't justify the cost of building this new computer. Second, if you put error correction on top of it, right, and quantum clock time usually is slower than the classical clock time, this quadratic speed up might be actually washed down, and we don't get a speed up in practice, right, in the end. There is, of course, many other, right, like there's a lot of work in other examples. These are the most famous ones. But definitely, it's the case that it's being shown hard to find large quantum speedups, right? Especially once you consider this kind of end-to-end analysis, right, where we really want to think about some, practical considerations since Shor's algorithm. All right, one class of examples where we do think that there might be these exponential speedups and might be relevant, right? So like, very good targets for relevant quantum applications goes back to the original idea of quantum computing by Feynman in the 80s, and that's the idea of quantum simulations, right? So there's this very well-known quote by Feynman. He said, okay, if you want to make a simulation of nature, you better make it quantum mechanical, right? Just, we know it's very hard to simulate quantum systems. We know the cost, in the worst case, grows exponentially with the volume of the system, the number of particles there. So let's just build a quantum computer to simulate the quantum systems. So how to make this more concrete? Well, usually, right, we have a Hamiltonian describing the system. Let's just assume that this is a Hamiltonian over n, capital N sites. Each site can have, a boson or a fermion or a spin. Let's just assume for this talk is a spin half particle. So you have, like a Hamiltonian, which is given, you can diagonalize it. So you have some eigenenergies, E sub j. It has some eigenstates, ket E sub j. And you like to understand some physical properties of this model, right? What are these physical properties? Well, there's many interesting things that you might want to compute about this model. One is just dynamics, right? So you just time evolve the system on some initial state, you compute some expectation value, and you're interested in understanding how this expectation value changes in time. And so this is called, like, this is the dynamics problem. And this dynamics problem, quantum computers, they work great, right, at simulating it, which is the original vision of Feynman. So for example, right, so we know we can simulate, right, this unitary operator e to the IHC for any time-independent Hamiltonian, local Hamiltonian, or sparse Hamiltonian even, with this number of quantum gates, linear in time and linear in the norm, right, in the total energy of the Hamiltonian. And so this is like, this is optimal as well, so we understand dynamics really well, right, and we do think for dynamics, quantum will give an advantage, right? So for some Hamiltonians, some of them we can even prove that unless something very unlikely happens, for example, you can factor a number, that there is some Hamiltonians for which this dynamics is out of reach classically. So that's great, but if you think about in practice, right, like properties that we want to compute from quantum systems, dynamic is one of them, but it's not the only one, right? And one that is even more computed and that is more relevant sometimes for applications is equilibrium properties, right? So what happens is that, like many times, if you have like a molecule, right, or a piece of a material, many times we're interested in the electronic states, right, of those. And because, the energy scale is like, electrovolt, for example, the system will very quickly equilibrate towards a state close to the ground states, right? Just because of the, at room temperature, right? So the ground state, right, the lowest, the eigenstate corresponding to the lowest energy, this E sub 0, is a very important state for, electronic states, for example. Usually, right, the molecule or material will be in this ground state, right, in the world. So we're interested in this. For some other, like a vibrational state, for example, right, or for molecule, right, or rotational states, then at room temperature or at temperatures that we care about in nature, the energy gap is not that big, so then you have a thermal distribution, right, over at equilibrium, a thermal distribution over the, the energies that you have there, and the right state, therefore, is this what we call the Gibbs state, right? Is the exponential with some inverse temperature beta of the Hamiltonian, the matrix exponential. All right, so can quantum computers help to compute, like properties on those equilibrium states, right? That's the question now. All right, so let me just mention a couple of examples of the simulation problem that we care about relevant to energy, right, because of this workshop. And they are kind of well-known examples that people like to talk about. One is both of them involves to computing properties of some complicated molecules that we cannot really simulate them classically. Of course, it's always a game, right, between quantum and classical. The classical people are always coming up with better simulation methods, right, and make it harder for quantum, right? But so even Femoku, there is like last month better classical algorithm methods from Gardner Chen's group for doing that. But still, it seems to be a difficult computational problem. So the Femoku molecule is this molecule that I put in here. I don't want to describe what it is, but it's kind of a big molecule. It seems hard to simulate classically. And people care about this molecule because it's kind of a key element of this nitrogenase enzyme, which is a way that some bacteria, right, produce ammonia in apparently a much better way than we know industrially how to do it, right? So if our goal is to produce ammonia without, spending, I don't know, like 2% of the worldwide energy, right, as we do today, maybe if we understand Femoku better, we could do it. Of course, it's always like a maybe, right, because this is, it's like research, right? So the quantum computer will be like a research tool, right? So you just, try it out on this molecule, you change it a little bit, you see how it behaves, right? And there's no guarantees, but that's one example, right, of might be relevant to energy. Another one that might also be relevant to energy is these three molecules that I list here. And they are interesting molecules because when they interact with lithium ions, they are the basis for lithium-based batteries. And they also is a complicated process to simulate classically, this interaction. So that's another example where, maybe if we have a quantum computer, we can model this better. We can, change things and see how it works, and maybe get better batteries, right? Again, big ifs here, but right, this is where we see quantum computers eventually potentially helping the development of more clean energy, right, or more cheap energy, and storage as well for energy. All right, so how, if you think about now this static problem that I mentioned, right? So I want to understand a property of the ground state, right, the lowest energy eigenstate of a many-body Hamiltonian H. What is the typical way of doing that? Well, the typical way is using this quantum primitive that is called quantum phase estimation. This was proposed by Alex Kitaev in 95, and the story goes that Alexei was in Russia, right? He heard about Shor's result that I mentioned before, but he didn't have access to the paper. It was like 94. But he said, quantum computers can factor, so let me try to derive this myself. And he managed to derive it in a novel way, and different from Shor, using this quantum phase estimation. So he developed that to find a quantum algorithm for factoring. But these days, this is also very used for all kinds of applications, including this simulation problem. So what's the idea? The idea is that you have this circuit here, right? So you have a Hamiltonian H. Each one of these U's is just a time evolution of the Hamiltonian H for time 1. And then you prepare all some ancillas and ancillas in the uniform superposition, right, over all bit strings. And then you have suppose you have some eigenstate here of some state psi, right, which is it can decompose as a sum of eigenstates, a linear combination of eigenstates of the Hamiltonian. And then, condition on the first ancilla, you time evolve, you apply u. The condition on the second one, you apply u for time 2. Then on the third one, u for time 4, and up to u for time 2 to the n minus 1. And then you apply the inverse quantum Fourier transform here. What you can show is that this quantum circle is doing the following. So if you start with a linear superposition, right, over energy eigenstates of the model, the quantum phase estimation gets in this other register, right, this ancillar register, some estimates of the energy associated to that eigenstate, right? So if you have eigenstate Ek, you put in this register some approximation of the eigenvalue associated to this eigenstate. And the approximation is in two ways. First is not exactly the eigenenergy, right? The eigenvalue is approximation of the eigenvalue. And second, there is some dispersion, right, over it. For Ek, you might have nearby eigenvalues as well, right? So there is some probability of error here as well. So it's just like a very approximate way of writing, but it's essentially what it's doing. Okay, why that's useful? Well, because then you can do the following strategy, right? So suppose you are given some initial state, psi, right, as the one here. You have just a way to prepare some guess states for your eigenstates. You run phase estimation. You measure the second register. And then you only accept if you get the energy associated, some energy, some measurement close to the minimum energy, right? And if you don't know the minimum energy, you can just guess and do binary search. That's easy. So this gives this kind of canonical way of preparing ground state, for which a lot of work is based on, and there's a lot of resource estimates for this, which is the following result. Quantum phase estimation can prepare a good approximation of the lowest eigenstate of the many-body Hamiltonian with error epsilon in time 1/epsilon, and the overlap of your initial guess states with the ground state squared. Why this overlap? Well, because this is the probability, right, that you measure the energy here in the lowest one, right? It's like C0 squared, which is this overlap. So that's great. So there's a lot of work, as I mentioned, analyzing this quantum phase estimation and getting gate counts for some concrete models, like Fermi-Hubbard, this Fehmoku molecule that I mentioned, and many others, like even in kind of high energy physics, like Schrödinger model. But there is some issues with this. So first is what we know in physics called like the orthogonality catastrophe, right? And this is just that when n grows, right, when you have like many particles in your system, almost every state will be orthogonal from each other, right? So you can change the physics very little, and the states will be completely orthogonal, right? Just because the dimension of the Hilbert space is growing exponentially, right? So what this means that for large capital N, large system size, might be very hard to come up with an initial state with a psi, right, your kind of guess state, which has no negligible overlap, right, with your true ground states. And this is kind of a given here, right? So you just assume that you have a good way to generate psi for which this overlap is not too small, right? Because if the overlap is too small, then the runtime will just, right, grow, right? So if, as typically happens, if the overlap decreases exponentially in the system size, this algorithm will run in exponential time. They won't be good. Second, and this is not about this particular algorithm, but that's just something to know. There won't be a general algorithm, right, for simulating ground states, because in the worst case, this is QMA hard. It's like the quantum version of NP, right? So it's an extremely hard computational problem, right? So there is, whereas in dynamics, we can always, right, simulate the dynamics efficiently on a quantum computer. There is no way we can prepare this ground state efficiently on the quantum computer in general, right? So you need more assumptions. For example, that you can prepare a good initial guess states. Second, this quantum phase estimation is a very what we call a global algorithm, right? So you prepare a state that has a good global overlap with your target state, right? Then you just measure the energy of that one and post-select on getting the right energy, right? Using phase estimation, which is also not, it's kind of a global algorithm, right? Where you may control evolutions of the whole Hamiltonian for some time. So this is not how classical methods work, right? For many-body physics, right? Where they are kind of local algorithms usually, like, density functional theory, or quantum Monte Carlo or tensor network algorithms, they're all like kind of you minimize something locally here, you go to the next one, right? You go back and forth. And this locality, I think, is important, right, to get something that works well in practice. And second, of course, this is very specific to ground states, but we also like something that works at non-zero temperatures. So we might need a generalization of this method. All right. So maybe we want to do more than quantum phase estimation. But then I think one objection is say, okay, but why you care about this, right? So we know in nature, right, dynamics is all there is, right? There's always the Schrodinger equation, and this is really dictating everything that happens in the universe, right? And that's true. So the question is, can we just follow Feynman and simulate nature as maybe nature does itself, right? Which is just dynamics, right? And the equilibrium just emerge from, is a emergent property of the dynamics of the system interacting with a much bigger heat bath, right? So maybe what we should do for equilibrium properties is not to do phase estimation, but just to model the dynamics of the system interacting by some interacting Hamiltonian HI to a big bath at some temperature, inverse temperature beta. And then if you just run these dynamics for long enough, and we trace out the bath, we get the thermal state on the system, right? And then just setting up beta to be sufficiently big, we can prepare the ground state if you want, the ground state. So that was proposed, for example, Terhal and Divincenzo in 98. And it might be a good way, actually. But there's also some issues with this approach. One is that we don't know the size of this bath, right? So this bath might need to be very big, right? Especially in early fault tolerance, right, where we have quantum computers that maybe have error correctors implemented, and we can run long circuits, but the number of qubits might still be limited, logical qubits. That might be an issue, right? Even long term, that's not how we do for classical systems. We'll get to that. But this having to model this big bath, that's a worry. And second, and I think that's very important, right? If you do something like, if you want to understand like some chemical reaction, right? So how we usually do it? Well, we treat the electrons quantum mechanically, but we don't want to treat the nuclei quantum mechanically, right? Because they're very heavy, they're classical. So for the nuclei, we want to do like molecular dynamics classically, and for the electron, we want to do like density functional theory or quantum Monte Carlo, right, quantumly. And if you play this approach, it's unclear, right, how you break quantum and classical with this bath, right? So we might not want to treat the whole system quantumly. So that's another limitation of this, just do dynamics all the time. So what happens classically? So classically, a new simulation method, right, was developed that kind of addresses this thing of not having to simulate the bath, which is inefficient. A long time ago, like in '53, right? And it's a very famous paper where they developed what we call now the Metropolis sampling algorithm, and it's a very interesting paper to read. I think it's very easy to read actually. So I recommend if you're interested in this kind of problem. And the title is like Equation of State Calculating by Fast Computing Machines. Where it was early days of computational physics as well. That makes it even more interesting to read. And I think the authors, they knew that they had something, I guess, important, right, when they wrote this paper, because they write this introduction, right? It's a great introduction. It says, okay, the purpose of this paper is to describe a general method suitable for fast electronic computing machines of calculating the properties of any substance which may be considered as composed of interacting individual molecules, right? So it's like a very bold claim, right? Okay, we show you how we can simulate any molecule, right, or any substance, right? So probably they're exaggerating a little bit, right? That's fine. But indeed, it's a very useful method, right? So this has been used, right, in the last 50 years all over physics and chemistry and beyond, right? In computer science and in AI, right? And that's just some examples, right? You can use Metropolis to study critical phenomena, to study polymer physics, protein folding, simulate annealing, right? And even quantum, with quantum Monte Carlo, if you don't have a sign problem. So what is this algorithm? It's a very simple algorithm, and probably many of you know it already, but let me just remind you how it works. So it's called metropolis sampling. Sometimes people also call it global dynamics. And let me use the IC model as an example, but it works for any classical model that you want to use. So the IC model is this Hamiltonian over here, right? You just have some interaction strength J, and then you have classical spin halves, right? 0 or 1, or actually 1 minus 1, xi. And they interact, for example, on a square lattice, like nearest neighbor interaction. And what is the metropolis rule? So the metropolis algorithm is like a random walk over the over the spin configurations, such that if you just run it for long enough, you start sampling from the thermal distribution of this Hamiltonian at some target inverse temperature beta. And how is this random walk defined? Well, it's defined by the metropolis rule. This rule is the following. It says the following. So in each time step, you pick a random spin, right, out of the capital N ones that you have, and you're going to flip its value, but you flip its value with a given probability, and the probability is the minimum between 1. So, if you flip the spin and the energy goes down, you always accept. But if you flip the spin and the energy will go down, you will only flip with probability given by this function here that I wrote. And what is this? This is the ratio of the Boltzmann factors, right, of the two energies, the energy that you have now and the energy that you have after, flipping the spin. So this defines a Markov chain, right? So you can just, right, given a configuration, there is Y, the Markov chain gives you the probability of going to a configuration X. And you can show that this Markov chain, the stationary distribution, which is the distribution that you get eventually if you just apply this Markov chain for long enough, is the Gibbs state that you care about, this guy here, right? So there is some important features of this master equation of this Markov chain. First is satisfy the tail balance, right, which just tells you that at the stationary distribution, this process is stationary, right, meaning there is there's a reversibility here. The probability of going to X given Y, if you're in the stationary state, in the Gibbs state, is the same as the probability of going to X from Y. Is also local, right? Each time you just choose one site and you flip this one site, condition just on the value of the neighbors, right? Because it's a local Hamiltonian. So this ratio really only depends on the site and its neighbors. And second, and this maybe it's a little bit harder to see, but it's also the case, it kind of mimics, right, the coupling to a heat bath, right? So kind of you're trying to model this process that nature is doing, but without having to include the heat bath directly, right? Just looking at the system. Just by choosing the metropolis rule to be this one, right? All right, so this is great, right? But why maybe this paper, right, from Taylor, right, and Metropolis and others, why they were maybe overselling it a little bit, right? Well, it's because this method doesn't really work for every substance, right, or for every model, and that's because there is an important parameter of the Markov chain that we have to understand, which is the mixing time of the Markov chain, right? So given any Markov chain, P, X given Y, the mixing time is defined as the expected length required for a random walk to approximately converge to the stationary distribution, right? So we know eventually we'll converge to the stationary distribution. This is guaranteed by this detail balance condition that the Markov chain, the Metropolis Markov chain satisfies. But we don't know how many steps we need, right, to converge to get close enough to the distribution. And this number of time steps that we need, this is the mixing time. And this mixing time, actually, this is a very interesting area, right? There's a lot of work on this, both classically and now studying quantum. It's usually a difficult subject to really understand the mixing time of some process. But we do know that sometimes this mixing time is pretty small, so you converge fast. And then we do know that sometimes it can be actually very, very big, and then Metropolis will just fail. You won't be able to converge. So here's one example, again, the IC model, the ferromagnetic IC model on a square lattice in 2 dimensions. You see that the mixing time will depend on like the on the phase transition of the model. So above there's a phase transition in the 2-dimensional IC model. Above the phase transition, the mixing time is very fast. It's like logarithmic even in time, and below the phase transition, it becomes exponentially long. The mixing time just takes a lot of time, and the algorithm won't be efficient. So this is like some plots, right? So like below the phase transition, we are in some disorder phase. Sorry, above the phase transition, we're in some disorder phase. There's like a unique Gibbs state, right? Because there's no symmetry breaking here. Metropolis will converge in n log n steps, and if you parallelize Metropolis, right, just to have many flips in one round, like other n flips in one round, then it actually converges in log n steps. And there is exponential decay of correlations, and everything is simple. At the phase transition, that's a little bit more subtle. Below the phase transition, then there is bemagnetization, right? The spins can be all up or down, and this just confuses Metropolis, right? So Metropolis becomes exponentially slow. It takes exponential time, actually exponential square root of n steps to converge. One of the two phases will dominate, right? Each time you run. There is long-range correlations, and there is, in the case of Ising model, two actually Gibbs states, right, in the infinite volume, right, because you can have a fixed magnetization either up or down. Again, if you fix magnetization, then things are fine again, right? So this is just one example where what is the whole story classically, just to sum up. We have Metropolis describe very well how you model interaction with a heat bath without including the heat bath, because it mimics the physics, right? Is a very good algorithm. It works very well in practice. It's not like a panacea that works always, right? But when it doesn't work, it's because actually there's something about the physics which says that it shouldn't work, right? Because, for example, there might be a symmetry breaking, and there you have to do something. You have to fix the symmetry breaking, for example, right? And when you do, then it starts working well again. All right. So then, great. So we have a very good algorithm classically, right, that solves this kind of equilibrium property. And now the question is, can we make it quantum, right? Can we have a quantum analog of Metropolis, quantum Metropolis sampling? So this is a problem that people have been studying in quantum computing for a long time, for like more than a decade. And I'll mention some important results soon. But it's a tricky problem. It's not like straightforward to really generalize classical Metropolis sampling to quantum Metropolis sampling. For a few reasons, there's a few challenges. Let me mention 3 of them. The first is that in quantum mechanically, we don't really know the eigenstates, right? I'm giving you the model, H, but these eigenstates, they'll be these complicated entangled states, right? And if you are at low enough temperature, the whole problem is to prepare the ground state that's, right? So, classically, you could just have a bit string, these are the eigenstates, we just flip one of them, we go to another eigenstate, everything very simple, there is no entanglement. But that's not the case for the quantum model. So how we address this fact that the eigenstates are non-local and they are non-explicit, right? Because we cannot write them down. The second is that also the energy, we don't quite know it, right? So classically, given the eigenstate, which is just a bit string, we can just compute the energy very efficiently, right? It's very easy. But quantumly, there will be this issue that during your algorithm, whatever you try to do for quantum Metropolis, you might not be always in eigenstates, right? Because you cannot even prepare eigenstates. You might be in some superposition of eigenstates. And therefore, the energy won't be well-defined, right? The energy will only be well-defined after you measure and have perturbed the states, right? So classically, you can measure with no disturbance, right? And you just from an eigenstate, which is a very simple object, you can get the energy. That's not the case quantum mechanically. And second, in Metropolis, it's very important this rejection step, right? So sometimes you reject the move and you do not change the bit string, right? But quantum, again, that might be tricky, right? Because, again, if you make a quantum measurement to see, right, if you accept the move or not, you have disturbed the states. And if you have disturbed the states, you might not be able to go back to the original one, right? So classically, after update, right, we can undo it, just, keeping a copy of Z. Quantum, we cannot keep a copy of the eigenstate in the algorithm, right? At least it's not clear how to do it. There is no cloning and so on. So this rejection is kind of a challenge. Nonetheless, in 2011, Teme and collaborators, they did propose and they did find a very interesting way of doing quantum Metropolis sampling. So their result was that there is a version of Metropolis on the eigenstates of a many-body Hamiltonian, where you use quantum phase estimation to compute the energies and to implement this metropolis rule to see if you accept or not. It's very non-trivial results, and it also means that it's a very complicated algorithm because you have to implement this rejection step quantumly. And for that, they use a trick due to Marriott and Watrous, where if you just make a two-outcome measurement, right, you can't have this kind of unwinding, right, procedure. But it was kind of messy, right? So definitely, I think was like a very important result. But first, there was also some drawbacks. First, the final algorithm with this rejection step was quite messy and very costly in terms of like gate counts. Second, this algorithm use this quantum phase estimation, which is not a very physical way of measuring energy, right? It's like a very nice algorithmic way of measuring energy, but it's not how nature does it, right? So it does not mimic the coupling to a heat bath that the classical metropolis was mimicking. And second, actually, there was some subtle issue in the analysis that this paper presented, where they assume a version of quantum phase estimation which actually doesn't exist. So there was like a gap in the argument. Then more recently, like I guess 2 years ago, Jiang and Irani, they were able to come up with a new version of this result by Tembe where they fixed this issue. So there is now a fully rigorous version that works of this algorithm. But it's still these first 2 points, right? I think it's something to have in mind about it. All right. So then I say, okay, so that's nice, but that's using quantum phase estimation, and I want to avoid that. Is there a way of doing kind of open quantum systems approach, right? What is the quantum open system approach? Where we like on a piece of paper we consider the coupling to the heat bath, right? But this interacting Hamiltonian has to be very weak, right, for the system to have a well-defined Hamiltonian and be in the thermal state. Let's just derive a master equation for this process, right, where we trace out, right, the bath to get a Lindbladian, and this Lindbladian is what we try to implement on a quantum computer. And there is good ways to implement the Lindbladian, that's fine. And in that way, we can get an algorithm that is like more physically motivated, right? And this was attempted even before quantum metropolis. Like there is these results from Davis, or also it's called like Davis generator from the 70s. And what Davis did was the following. Let me see. So he considered exactly the situation where you have a system with a very weak Hamiltonian coupled to a bath. The bath at some inverse temperature beta. This is like some interacting Hamiltonian with interacting strength lambda. And then he derived a master equation for this process. So he derived this is a normal master equation. There is like the unitary dynamics given by the Hamiltonian, and then there is usually a lamp shift correction, right, to the original Hamiltonian. And then you have, right, this is just a normal, like a general Lindbladian with some jump operators. And he could derive that these jump operators, they are very intuitive, right? So they are just in the energy. If you just write them right in the energy basis, they just connect the eigenstates of energy. Or I'm sorry, this should have been. This is a typo. These two should have been E sub I cat bra E sub I. Sorry for the typo. So they just connect two energy eigenstates, right? You can go from energy eigenstate Ej to Ei that have energy difference given by omega. This is what the A omega term does. And then this function, you have to put these constraints such that the system satisfies the tail balance, now quantum tail balance, right? Which is this operator equation here. And this guarantees that the Gibbs state is the stationary state of this Lindbladian, of this dissipative quantum process. So that's very interesting, but maybe you can be a little bit suspicious about this, right? Because you say, well, it's these energies, right? They might be exponentially close one from the other, right? Because it's just a model that has exponentially many eigenvalues, but only right? If it's a system of capital N spins, you have 2 to the n eigenvalues, but you only have extensive energy capital N, right? So how you fit 2 to the n numbers into an interval of size n? Well, the gaps must be exponentially small, right? So this means that these jump operators, they are distinguishing, right, like energies which are exponentially close one from the other, right? And indeed, this is a catch. So Davis have to assume some kind of weak coupling regime where lambda is much smaller than the minimum energy gaps of these eigenvalues for the derivation to work, which means that this is fine, and this gives a limblazzi, right, that converges. But in it only mimics what the physics is doing in some unphysical weak limit regime, right, where the coupling is exponentially small in the system size. Right, so this is what I was saying in words. You only have an interval of size O(n), but we know that the minimum energy gaps have to be exponentially small in n because there is exponentially many of them. So Davis provide rigorous derivation, but this derivation is in an unphysical regime, right, where sorry, let me go back, where the weak coupling is exponentially small in the system size, right? Yes.
N is the size of the reservoir as well?
No, and capital N is just the number of particles of the system. Here, is completely independent of the reservoir, right? The reservoir we have traced out, right?
Okay, then I'm confused, but carry on.
Yeah, okay, yeah. Then you can say, well, okay, maybe it's unphysical derivation, but who cares, right? I do have a master equation that has the Gibbs state as the stationary state, so that's great. So I can just run this on the quantum computer. Unfortunately, no, you can't, because there's a price you pay, right? So because you're resolving these energies, right, like to this exponential precision, right, it means that you just cannot implement these jump operators on a quantum computer efficiently, right? So they also have this Fourier decomposition, right? So you can implement them by some time dynamics, right, for time t, like the Fourier transform. But this Fourier transform, you just need to run this Hamiltonian for arbitrarily long times to do it, right? So Davis is very interesting. It does give a master equation for every many-body Hamiltonian whose stationary state is the Gibbs state, but it's unphysical and we cannot implement on a quantum computer. All right. So then the work that I want to mention, right, with like Anthony Chen, Mike Kassarian, and Andres Gillian, and it's a work like it's already like a few years old, and more recently we had something like summarizing the main results that we got, is trying to get an efficient version of Davis generator, so efficient quantum Gibbs sampler that we think is like a natural one to consider, and they have some advantages over the original quantum metropolis. So we show that you can write a master equation of this form, same as Davis, that prepares, that has the following properties. So first, this function will be similar to the one that we have for Davis, right? It's just some function to guarantee kind of quantum detail balance. Doesn't matter too much what it is. The jump operators will be similar to the Davis ones, but now we have a filter function here, f of t, right? So, and this f of t is actually a whole set of functions that works. But for concreteness, let's just focus on one here, which is just some Gaussian, right? So basically, we just put some Gaussian filter function on this Fourier transform to define the jump operators. And why that's helpful? Well, because this function is fast decaying, so this means that for long times the contribution to the integral is very small, right? So we can just truncate, and we can just this gives a way to implement this A of W efficiently on a quantum computer. This Hamiltonian H is some kind of like lamp shift version, right? Of this lamp shift correction appears again. But the way we derive is just kind of, we do reverse engineering, right, over what we need to get something that works. So I don't claim there is a physical derivation of this. Oh, this is a type. This dA should be the same A that we had before. So it should just be A. Doesn't matter what it is, right? It's a little bit complicated, but it's some kind of like, we make it such that the limblazzi has the properties that we want. And what are these properties? Why we think that's an interesting construction? First, we can show that L is quantum detail balance. Meaning that the Gibbs state, right, will be the stationary state. So eventually, if you just run this master equation for long enough, we prepare a good approximation of the Gibbs state. Second, because we have this filter function, f of t, we can use Libre-Opson bounds, and we can show that this A omega, they are quasi-local whenever H satisfies a Libre-Opson bound, which is the case for every local Hamiltonian, for example. So I think that was kind of an open question. Right? Can you get a limblazzi which is quasi-local and can prepare Gibbs states? The answer is yes. And second, because this AW, they are quasi-local now, we can efficiently simulate L on a quantum computer, right? And therefore, it does give a quantum algorithm for doing it. And okay, so how you do on a quantum computer? So these are the circuits. Maybe I won't get into the detail of the circuits, but this is the claim. The claim is that to implement this quantum channel, right, which is e to the power of Tl, right, just the time dynamics of this Limbladian for time t. This can be implemented on a quantum computer with the following resources. So order t times beta Hamiltonian H simulation time, right? You just run whatever algorithm you're using for Hamiltonian simulation, like Trotter or qubitization, whatever you want, for time t times beta. We need a constant number of ancillas, and we need order t 2 qubit gates in addition to that, which are pretty all reasonable and actually optimal. You can show these are all optimal kind of scalings. And they're much better than what you get if you want to just use the original Metropolis, right, or the recent version that fixes this issue that they had in the original paper. What is the total cost to one Gibbs sample, right, to prepare the Gibbs states? Well, it will be beta times T mixing, right? What is this T mixing? It's just this mixing time that I mentioned before, right? That's an issue classically. That's also an issue quantumly, right? That's something that we have to, figure out model by model if this converges fast or not. And for ground states, we can replace beta by 1/gap. Right, so now, if you focus on ground states, before we had this initial gas state, right, that you have to have good overlap with the ground states, that might be hard to prepare. Now we have something different, right? We have the mixing time of this master equation, right? Again, sometimes it will be very big, right? So again, it's not like free lunch here, but I do think there might be is a little bit more physical, right, than these initial states. Maybe I only have a little bit time, so I'll jump this. And I just want to mention some recent work since these two papers that we posted a couple of years ago. So first, there is a richer set of Gibbs samples with other filters function, as I mentioned, which is interesting work. There's a lot of them, and we have a classification of them. There is also proofs of rapid mixing for some interesting cases, like, for example, for constant per large enough beta, every local model will have rapid mixing. In one dimension, every model has rapid mixing. In quasi-free models and weakly interacting models, there is always rapid mixing. They're not systems that we expect to be hard classically, right? But it's nice to see this. For sparse random Hamiltonians, they are rapidly mixing, and they might be classically hard actually. For models satisfying ETH, right, this eigenstate thermalization hypothesis, we can show rapidly mixing as well. There's also variants that can be derived from weak coupling from the heat bath, really trying to go back to this Davis derivation, but trying to make it physical. There is versions of this master equation that you can derive. There is characterization of metastable states as well, which is states for which when the mixing time is very big, the system will go to what we call metastable states, and it has some interesting properties. And there is some results on the equivalence of rapidly mixing in time and space, meaning if you have fast decaying correlations in space, you have rapidly mixing in time. All right, so just to end, to make Feynman's vision practical, right, we need quantum algorithms to simulate thermal physics. I think this new family of Gibbs samplers that I mentioned, they are promising, but there's some open questions. So I think the main ones is, first, can we get reasonable quantum gate counts for models of interest, right? So we should just take the Femoku molecule or whatever you want to do, get the gate count, see if it's something reasonable, given the clock speeds that we expect from quantum computers. This hasn't been done yet for this algorithm, and I think it's an interesting problem. Second, can we identify a model where this gives quantum advantage, right? Where we can kind of argue that the mixing time quantum is not too big, but classically is out of reach. That would be interesting as well. And second, can we argue that this model faithfully mimics coupling to a thermal bath in nature, so that it's fast mixing whenever thermalization is rich in nature, and when it's not rich in nature, right? When it's not fast mixing, that the set of metastable states that it reaches when thermalization is low corresponds to the metastable states that we have in nature, right, when nature cannot thermalize as well. So that's all. Thank you for your attention.
Thank you very much. I do know that the quantum Gibbs sampling is trending, and I was wondering as you were speaking, are you working on it because it's trending, or is it trending because you're working on it? Quantum Gibbs sampling, anyway. Andosh confirmed it to me that that's the hottest topic in algorithms right now.
Should I answer it, or is just a...
If you dare, yeah.
I don't have an answer, but I have to say, I'm not doing it because it's trendy. I have been doing that for 15 years when it was not trendy. So
Okay, so it's trending because you've been doing it.
that's-
Okay.
I think it's trendy because I convinced Chen, Anthony Chen to work on it, and he was able to solve the problem, right?
Okay,
He and Andras.
So we just said Anthony Chen is an influencer. I'm talking like a bad journalist, right? Okay. Can you go back to the slide with the table? That was the most fun slide that you skipped.
Sure.
Can you just compare briefly Quantum Metropolis and
Yeah.
today?
Yeah. Thanks for the question. Right. So this is a table. There is like the Davis generator that I mentioned. This is the Quantum Metropolis from Teme, and this is what we propose. So these are things, right, that we want, like the tail balance, for example, which means the given state is stationary. Davis has it, right? Quantum Metropolis doesn't have it, and this new proposal has it, Quantum Metropolis has approximately, right? It's a little bit messy. This detail balance, if it's approximate. Local, right? It's a local algorithm in space. Davis is not, right? It's very non-local. Quantum Metropolis is very non-local, and this new one is local or quasi-local. If you can efficiently simulate on a quantum computer, Davis you can't. Quantum Metropolis you can, approximately, and this one you can as well. Simple enough, right, that you can actually prove stuff, right? As I showed these people proving rapidly mixing in some cases. Davis, there was some results actually, so you can sometimes. Quantum Metropolis, no one was able to do it, right, because it's just pretty messy, and now there's a lot of works that people can do it. And is it physically motivated? Davis, kind of, right, but in a very kind of weird limits. Quantum Metropolis, not really, right, quantum phase estimation, I don't think nature uses it to do anything. And the one I propose, especially the later versions, I think one can argue that it is physically motivated.
Thank you. We started the session at 10:05. Let's discuss until 11:05.
Hello, thank you for the talk. Probably an idiotic question, but why go to such lengths to simulate a bath? Because a thermal bath is not something the world is particularly short on. So can't you have something like a photon cavity that you can heat to whatever temperature you want inside your quantum computer? Have a couple qubits, maybe even one, strongly coupled to it, and then you can couple that qubit to whatever you want.
Yeah, that's a great question. So I think what you're saying works sometimes for analog quantum simulations, right? So suppose, you have your ion trap there where the Hamiltonian, right, naturally implements some, like transverse field Ising model, or you have some optical lattice, and then you just have some temperature, right, of your experiment, and then indeed there will be a heat bath at that temperature in your experiment. But a few things. So suppose now you are, first you might not control, it might be hard to control the temperature of that bath, right? So that might be one limitation. You would like to, have that for any temperature that you want. But I think the main reason for considering this is that eventually we want to simulate any model that we want in a universal way on a quantum computer, right? And for doing that, we know we need to do error correction. And when we do error correction, then the bath will not act in the way that you want it to act, right, on your system, right? So the bath will cause decoherence, but might not necessarily thermalize your system to the right logical Gibbs state that you have there, right? Because in error correction is this very particular method where you have some logical qubits out of many physical qubits, and it's not the case that the Lamblages that you have for the physical systems, right, at the physical level, translate into the right Lamblages at the logical level that will thermalize the system.
Okay, maybe I'll ask more about it later.
Sorry, so, thank you for the talk. My question is that I don't know if you know some attempts to solve the problem of non-locality in the Davis generator, which is called partial secular approximation, because all this non-locality comes from the secular approximation.
Right.
And your generator is very nice. But if there is any relation with this partial secular approximation? Or?
Not that I know, and I might not be completely up to date on what you're saying, but what I knew was that, doing this partial secular approximation, you might get something local, but then you actually, it might not be like really a Lamblazian anymore, right? So it's like you have to approximate the Lamblazian condition, so you wouldn't really be, you wouldn't generate like a completely positive map, right? And do the time dynamics. In that sense, for example, you cannot implement on a quantum computer, right? Or you have to find a way to implement it. So I think that will be one different, right? Here is always completely positive, right? Everything we're doing, right? And the Lamblage is always preserved, right? and the approximation is more in the, in how you define the jump operators.
But your generator is just engineered, or you think it can be derived from the physical
Right.
dynamics? Or?
So this we didn't do, but then there was a follow-up, and let me tell you what they did, which is interesting. They consider an interaction of the system with a heat bath, which only has 1 qubit, but they consider the following one, so it's not completely what we want, but I think it's one step, where you refresh the bath. So you interact for a little bit, the system with 1 qubit bath, but then you reset the state of the bath very quickly. You do it again, you reset very quickly, you do it again, and then they could derive exactly this mass equation, but where the width of the Gaussian is like proportional to n, the system size. So then, it's a nice derivation. It's not what we want, because we want this width to be like proportional to, inverse temperature here. But I think it's going this direction. If you can really have a very physical derivation where we get something like this, is open.
Wonderful. Other questions, please?
Hi, Fernando, thanks for the talk. So let me see if I understand. So you are giving this Limbladian, but then you are thinking of a digital simulation, right? You have an algorithm with gates that implements this. So there is no bath or anything like this. It's just a circuit that implements that.
That's right. Yeah, that's right. I mean, yeah. So one might also be interested in just deriving a Limbladian that has these features and they prepare the Gibbs state. But indeed, on a quantum computer, you just implement this Limbladian using general algorithms for implementing Limbladian, right? Which requires some ancillas, right? Because you have to, implement. You have to kind of find the spring dilation of the channel, right? But indeed, it will be just a digital, circuit in the end.
Right. One more question, please.
In many of the classical simulations, one of the challenges phase is of bond dimension. And so do you encounter this when you increase the dimensionality of the system, say to 2D or 3D? Like, are there similar challenges in the quantum simulation?
Not for this hour. I mean, okay, so there will be, in the sense that even this example classic that I was mentioning before, right, where for the Ising model, right, of course, in 1 dimension is very, very easy, and then in 2 dimensions we know, right, that below the phase transition metropolis will just take a long time, right. Similar problems I think will happen quantumly. So quantum, you know, the result, right, a recent result that shows that in 1 dimension, this quantum metropolis will always, this version that we presented, we will always converge quickly. The mixing time will always be like constant. Sorry, the gap will be constant, the mixing time will be linear. And we know in 2 dimension already, right, we have hard models for which the mixing time, or the quantum algorithm has to be very long, right? So there is similar questions in that sense. But the big open question here, I think, is, okay, is there a case where the classical methods, they all fail, right, in 2 dimensions, or 3, but we can show that the mixing time of this is still like, polynomial, and the quantum will work efficiently. That, I think, is kind of open.
Okay, so there's a related question. In absence of classical reference point, how do you benchmark the results that you get?
I mean, this was like, we wrote some theorems and wrote some proofs, right? And this is, we didn't run, I mean, we run numerically very, very small, right? But you're saying for this work, or you're saying eventually when you have the quantum computer and we run it, how you specify it?
No, for the method that you have.
Yeah, no, this was just like, mathematical physics, right? We wrote this and we wrote the master equation and we proved that it has the right properties, right?
Okay, thank you.
Thank you.
So no comparisons, right, with the classical. We're benchmarking quantum for quantum.
Yeah, it was just like, you can actually have a theorem showing that these properties hold true for this master equation. Right?
Okay, I've been signaled that the session should end for good reasons. There's coffee waiting. Enjoy your coffee break. Thank you, Fernando.
Thank you.
So